Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll learn more about acoustic wave focusing and introduce a concept called geometric acoustics.
So let's get started. We've so far studied a point source modeling method for sound fields, and by understanding this method, it leads us to believe that our sound measurements will be different, whether we're close or far from a source. So what are the distinguishing factors of these sound fields? Well, there are three sound fields around sources. A, the location nearest to the sound source, is called the hydrodynamic near field. The hydrodynamic near field is characterized by acoustic energy that sloshes back and forth. The acoustic pressure is almost exactly out of phase with particle velocity, and the specific acoustic impedance is purely complex. The region B, that's further away than the hydrodynamic near field, is more than a few wavelengths away. This is called the geometric near field. Now, in the geometric near field, the acoustic pressure and particle velocity are nearly in phase, but the acoustic pressure amplitude does not decrease by the 1:r relationship that we're familiar with for spherical waves. And then finally, the area C is the genuine far field. And the far field is characterized by three distinguishing criteria. The first criteria is that we must be in the acoustic far field, which given the acoustic wavelength, R must be much greater than lambda, the wavelength from peak to peak is shown here. In this case, the acoustic impedance for this wave source gradually goes to rho naught C. And that's the interpretation. The acoustic energy in the far field is purely transmitting in one way. The geometric far field must also be satisfied for us to be in the far field. In this case, R is much greater than D, the characteristic dimension of the source. Here, the beam pattern is constant when we're in the geometric far field. And finally, we must satisfy the third criteria, which is the source size factor. Source size factor is that the radial distance R must be much greater than the ratio of the characteristic dimension d squared divided by the wavelength. And this assumes and assures that pressure amplitude decreases in proportion to 1:r. In practice, it's important to measure sound sources in the far field in order to have legitimate data. But we need to recognize that if we're too far away, we'll have bad acoustic pressure measurements because the sounds will be so low in level. What then is the characteristic in the near field? Well, we oftentimes take advantage of one characteristic in the near field for applications, and that's wave focusing. Focused acoustic waves are distinct than beam forming. Beam forming occurs in the far field. Wave focusing is when waves increase with increasing distance from the source. So in this plot, we're actually increasing an axial distance from the source, and at some point, the amplitude goes up. This will be a focal point where the sounds increase in amplitude with increasing distance from the source. Often that distance from the source is not very far, though. The sounds increase in amplitude at least up until the focal point, and we use wave focusing in many applications. Imaging, treatment, sound reproduction in outdoor environments, even novel ideas like levitation. Very interesting work in levitation being conducted right now. So the whole principle of wave focusing is in geometric acoustics. It's sometimes called ray acoustics. It studies wave propagation on the basis of lines that are perpendicular to the radiating surfaces. This is exactly analogous to geometric optics, and to a lesser extent, geometric electromagnetics. But let's understand a few examples to gather intuition about this practice. If we have a parabolic radiator that we sometimes see in electromagnetics or optics, sounds from outer space arrive on the surface of this satellite dish and are transmitted to this central receiver due to the fact that the transmitter or the receiver is shaped like a parabola. For the case of a sphere, sound radiating spheres will focus near the sphere center. This is quite intuitive. Received signals to a spherical surface, though, do not focus at the spherical center. But if it's radiated, it's one great way of focusing acoustic waves. We can also focus waves arriving from the far field using the similar principle that's used for light and electromagnetics. In this case, we use a parabolic reflector. And if we transmit sources from the center of the parabola, we generate plane waves. Whereas if we receive sources, the parabola will focus those sources to a point on the basis of acoustic reciprocity. Let's see this in practice. This is an example of a parabolic reflector and a sound source generating waves into it. What we see is that the waves become planar very quickly. And this differs than if that source was sitting on a hard-backed plane. We see at the far field of these sources, or at least many wavelengths away, the source in the middle is still highly spherical, whereas the source on the left is mostly planar. In this example, we see that parabolic reflectors generate plane waves without the need for the developed far field. In an additional example, we can take a hemispherical or spherical radiator. Here we see that the focal point is where the sound is increased for this hemispherical or spherical radiator. But we do see that the focal point is not exactly the sphere center. The sphere center is shown as the yellow dot in the animation, but the focal point is slightly increased in location than that yellow dot. And this is quite common. If we have a perfectly complete hemisphere, the focal point will, in fact, occur at the hemisphere center. So let's summarize what we've learned. We've learned that the sound fields around sources are exploited for different purposes. In the near field, we often take advantage of wave focusing and imaging. But in the far field, we're interested in transmitting or receiving signals over long distances. And in this case, we often are using the far field acoustics for imaging and communications. Geometric acoustics is an easy way to predict focal phenomena and design acoustic lenses. And we use similar concepts here as we do in optics and electromagnetics.
That's it for this video. In the next video, we'll learn how geometric acoustics is applied in the field of medicine with ultrasound.